Sample problem 2.3. Oxygen is the most abundant element in both Earth's crust and the human body. The atomic masses of its three stable isotopes, oxygen 16, oxygen 17, and oxygen 18, are given here, as are the relative abundances and the atomic masses. Calculate the average atomic mass of oxygen using the relative abundances given in the parentheses. Report the result to 4 significant figures. Okay, so when we look up a element in the periodic table, and I'm going to take hydrogen as an example. This number down here is called the atomic mass. The atomic mass is a measure of how heavy one atom of that element is. So when we see 1.01, what that essentially is telling us is that one atom of hydrogen has a mass of 1.01 AMU. Now, you have to be careful. It depends on what periodic table you look at. It's quite possible you could look it up and see a different number. .008, for example. This is still the atomic mass. It's just different number of sig figs. If we were to round 1.008 to 3 sig figs, it would round to 1.01. You may even see more sig figs for hydrogen. It might be 1.0079. Again, that's the atomic mass. It's just got more sig figs. It's got 5 sig figs instead of 4 or 3. Those are the atomic masses. Okay. Now, notice these numbers are not whole numbers. They're close, but they're not whole numbers. The mass of an atom is given by the mass of its nucleus plus the mass of any orbiting electrons. Electrons orbit the nucleus. And it could have more than one electron. The nucleus has protons and it has neutrons. And it turns out for every element in the periodic table, you can have what are called isotopes. And isotopes are atoms that have differing numbers of neutrons but are the same element. So for example, for hydrogen, there are 3 isotopes. Hydrogen 1, it has 1 proton plus 0 neutrons. Hydrogen 1, 2, 1 proton plus 1 neutron. Hydrogen 3, 1 proton plus 2 neutrons. Those are called isotopes. So these are the naturally occurring isotopes of hydrogen. In nature, there is no H4. There is no hydrogen with 3 neutrons. Only one with 0, 1, or 2. Okay. The third one, this one down here, let me give you names actually. This first one actually has a name. Protium is this isotope. Deuterium is the second isotope. Tritium is the third isotope. This tritium is actually unstable, so there's very little of it found in nature. But the first 2, protium and deuterium, are very commonly found in nature. Now, when you consider just those 2 isotopes for the most part, what you find is that around 99, I'm going to put around, 99% of hydrogen is protium. And approximately 1% of hydrogen is deuterium. And they have different masses. This one weighs approximately 1 AMU. This one weighs approximately 2 AMU. So they have different masses. But in nature, that's a mix of them. So if we want to measure the mass of hydrogen, and so we have a bunch of hydrogen atoms, here's what happens. So I'm just drawing lots of little hydrogen atoms here. 99% of them weigh 1 AMU, approximately 1 AMU, and only 1% weigh 2 AMU. So the weight, the average, let's not use weight, let's use mass. The average mass is between 1 and 2 AMU. It's closer to 1 because 99% of them only weigh 1, only 1% weigh 2. So it's actually going to be very close. An average would be very close to 1 AMU. And that's what we have here. If you look at that mass there, the atomic mass, it's very close to 1 because 99% of them weigh 1 and the other 1% weigh 2. The average of that would be 1.01. Okay? So here's what we're going to do in this problem. We're going to calculate what's called the average relative mass. And this is going to ideally give us the numbers that we see in the periodic table, the atomic masses in the periodic table. The way we do this is through what's called a weighted average. And if you're confused about weighted averages and you can't figure out how to do it, you could just look on YouTube and you'll find all kinds of videos on how to do a weighted average. Okay? So here's how you go about it. We're going to do it for oxygen. What you do is you take the first mass, I'll call it M1, and you multiply that by the percentage over 100. And then you add that to the second mass, and you multiply that by the percentage over 100. Then you add to that your third mass, which is multiplied by its percentage divided by 100. Now, these three masses, M1, M2, and M3, for oxygen, those are the atomic masses that are given in this problem. 15.9949, 16.9991, and 17.9992 for those three isotopes. The percentages, notice how the percentages are given for 16, 17, and 18? Those are the percentages we're talking about right here. So you take the atomic mass of each isotope times its percentage over 100. The reason you're dividing by 100 is to convert the percentage into a fraction, into a decimal value. So very straightforward. So we take the first one, which is what, 15.9949? I'll put it in parentheses. Times its percentage, which is 99.757. Over 100. Okay? You add to that the second mass, which is 16.9991. I'm not putting the units in just to save space. The percentage is like 0.038%, very small percentage. Again, you divide that by 100. Okay. You add to that the third mass, which is 17.9992 times the percentage over 100. Okay? those 3 percentages should add up to 100. If there were only 2 isotopes, we would just add 2 terms, not 3. If there were 4 isotopes, we'd add all 4. If there were 5 isotopes, we'd add all 5. For oxygen, there are 3. Okay? So let's go through the calculation here. 15.9949 times 99 point, let's figure out what this is, 757. Divided by 100. And you get 15.9560. Okay, now let's add to that the second term. 16.9991 times 0.038 over 100. .051847. Okay. Add to that the third term, 17.9992 times 0.205 divided by 100. 036898. .898. Okay. Now we add those together. 15. I'm going to use the numbers that I have here on the calculator. 15.95603. I put a couple extra sig figs in there, that's fine. Plus 0.051 847.255, 0.036 89836, and you get 16. Seems a little high. Let me check that, okay? 0.051 847.255 plus 0.036 89836 plus, oh, we got to get the first one, 15.956. Seems like a little high, 16.04. So what I'm going to do is I'm going to go ahead and check these calculations. I don't trust that that number is correct, so I'm going to go right through it again. And I'll show you why I don't trust it. 15.9949 times 99.757. Oops, divided by 100, sorry. 15.9560. That first one looks good. That one looks good right there. I suspect there's a possibility one of these I messed up, but let's see. 16.9991 times 0.038 over 100. 0.0, there we go, there's a mistake. 0.006459658. Now I wonder, Well, let's not do that. 0.00645 0.00645 9658. And then the last one might be right. Let's see. 036898. That's good. Okay. Let's actually just not even write anything with that one. All I'm going to do is point out that we are getting rid of this one. And that's going to change our sum, right? So let's go through it again. 15.956. It's all written up here. 15.95603 plus 0.00645 9658 plus 0.036 89836. Now we got something. 15.9994. Now let's go through the units. Here's what happens. The mass is in AMU. Percentages are unitless. So an AMU times no units is just AMU. Okay, now let's go through the sig figs, the significant figures, because this one's a little bit involved. We're doing mixed operations here. We're doing multiplication and division, but we're also doing addition. So the first step is to figure out in each of these terms how many sig figs we should have, and then add them together. So let's take the first one. The first one is multiplication and division, but 100 is an exact number, so we can ignore 100 because it's exact. We're only considering the measurements. So 15.9949 has 6 sig figs. 99.757 has 5 sig figs. The rule of multiplication division is the number that has the smaller number of sig figs. Your answer should have that many. So since there's only 5 here, we should go out 5 for our answer. So 1, 2, 3, 4, 5. So I'm going to put a line, it's called a bar. We put a bar over the last digit that's significant. Anything after that is not considered significant. Now, let's do the second one. The second one has, in its first measurement, 6 significant figures. But the second one only has 2. Remember, leading zeros are not significant, so there's only 2. So leading zeros are not significant, so the second one would be right there. 6 and 4. Now let's do the third one. The third one also has 6 sig figs, but it has 3 here. So 3 sig figs would be 1, 2, 3. So now what I'm going to do is I'm going to line up these numbers. And I'm going to put a bar over the last significant figure for each of these numbers. Remember, the 4 is the last significant figure here, and then 0.036 898. And our last significant figure is that first 8. These are addition. Now, the rules for addition and subtraction, what you do is you add them all up. Okay, let's come back. We got 4. I put 4, but we could put 388. Let's just go ahead and put 388 just so I can show you what's going to happen. There we go. Okay, the rule of addition and subtraction is that the answer cannot be known more precisely than any of the measurements. This one only goes 3 digits past the decimal point. This one actually goes 4 digits past the decimal point. So does this one. So the answer has to stop right here, which should be right there. So you round it. It's 15.999. 3 is less than 5, so you just truncate it. Just get rid of everything that's after it. And there's your answer. Answers in EMU. Okay? So that is the average atomic mass. Sometimes they call relative mass. It's relative because we're considering that carbon-12 is exactly 12 AMU. So it's relative to carbon-12. But the answer would be 15.999. Now remember, when I first had this number here, and I did the computation, and I came out with 16.004 or 16.04, and I said, hey, that's wrong. There's something wrong here. Here's how I knew it. Here's how you can check yourself. We know what element it is. Look it up in the periodic table. It's 16.00. So it's not 16.04. So if I do this calculation and I get 16.04, that's not even close to 16.00. So I know that's got to be wrong. So I went back and I checked and I found my mistake. It's easy to make little errors here, right? So this thing has everything in it. It has a lot of stuff. It has unit dimensional analysis. It also has significant figures. It has the different rules of sig figs, addition, subtraction, and multiplication, division, in addition to figuring out the relative atomic mass. So in a nutshell, all of these symbols that you see in the periodic table, so for example, if you see fluorine and it's 19.00, that's an average. It's an average of all the isotopes that are found in nature, a weighted average. And we would calculate that weighted average by taking the atomic mass of each isotope and multiplying that by the percentage abundance that's found in nature. Interestingly enough, these ratios, these percentages, the percentages vary depending on where you are. So usually these numbers are taken for the ocean because the ocean mixes. So they look at what the isotopic ratios are in the isotopic percentages are in the ocean because it mixes. So it's going to be the same throughout most of the ocean. If you look in the Earth's crust, it's actually a little different. The percentages are a tiny bit different because of the chemistry and geology that goes on the Earth. And you can look on other planets. So if you look at Mars, if you look at the percentages of oxygen on Mars, they're different than the Earth because Mars has a different history than the Earth. And so you can actually tell, it's almost like fingerprinting, you can tell where a rock comes from based on the percentages. They have found rocks in Antarctica that have percentages that match up with the rocks on the Mars, the percentages that are found in Mars, but not on Earth. So that tells us those rocks must have come from Mars. And you ask, well, how'd they get here? Well, probably something slammed into the surface of Mars millions of years ago, kicked up enough rock into the space that it actually escaped Mars and then eventually fell to the surface of the Earth, where eventually it was found in Antarctica.